students, welcome to our course Environmental Modeling and Simulation. In today's lecture, we are going to be discussing simulation. Simulation is basically when we want to see the different possibilities and different states of a reality, of a real situation, but want to do it much more effectively, faster, and cost effectively. And the way we do simulation now is computer based. So when we are simulating a system, what we are doing is we are trying to see the scenarios, we are trying to experiment with the real world, but not in reality, but by using its imitation. So today, what we are going to do is get an introduction of simulation, look at what are the different approaches for doing simulation. Note that since simulation is computer based, it requires mastery of certain computer languages, especially if nothing else, one should be really familiar with Java. We are not going to go into those computer programs that are used for simulation because there are many of them, but we are going to look at what the different approaches are and how they are useful in environmental context. So, in order to understand the real world scenarios, especially like environmental scenarios, one needs to understand that since there are multiple factors, the number of dimensions in a model is very high. This is something we covered in one of the earlier introductory lectures, is that when n becomes really big, n is really big than 1, then the models become increasingly complex. And these models are very hard to solve, to integrate if we are using ordinary differential equations. However, simulation using computers can be an easy way out for us to understand how the system will respond without making it too simplistic. Now remember, when we discussed how to write models, one of the things I highlighted was we want at least two basic things from any given model. One is that it should be simple enough to understand. It should be simple enough to simulate. It should be simple enough to do its integration, to look at its slope field, its phase portrait when we are solving it. And the other thing was that it should be a fair enough representation of what's really happening, and it should give reliable predictions. Now with simulation, we are less limited. The ability of our high-performance computers to simulate our systems has increased rapidly over past few decades. We do not have to overly simplify our systems. We can let them be complicated, and we can simulate the system. We can experiment using simulations. For different environmental scenarios, for example, activated sludge process-based wastewater treatment systems, we get simulation softwares who already know that how an ASP-based wastewater treatment system works. They have the basic processes that people can use, and then they can simulate different scenarios. What if the loading increases? What if the loading decreases? And other scenarios, for example, change in temperature, change in aeration, or polymer addition, depending on how the treatment is happening. Now, this is an example of simulation for a very specific scenario. In environmental systems, we have multiple scenarios. For example, we have weather. We have environmental crises like flood, drought. Each of them can have their own simulation scenarios. And then, of course, there is the mega one, the climate crisis. So we have simulation scenarios for climate crisis. What happens if we change our emissions? So we can answer questions like this, like what happens if we do A intervention versus B intervention? What will be the overall impact in the system? We can use our simulation. And I hope you understand now already that these simulation programs are extremely complex and the programming is not very straightforward. So as environmental engineers, environmental professionals, what is convenient for us is to purchase a simulation package made by computer engineers along with environmental scientists for very specific scenario or system that we are looking at, and then use it. Now, the danger with such an approach is that it becomes a black box approach. We do not know how the simulation works. We do not know how applicable it is to our system. And this is where the introduction that we are going to do in today's lecture and in the next lecture will help you understand how applicable the simulation is, what are the different approaches, and which approach would best suit the system that you are looking at. So now let's look at different approaches for simulation. What are the things that we need to consider? And obviously, very importantly, we need to look at validation of simulation. A simulated reality is an imitation of reality. It is not the reality itself. So if there's any error in the simulated reality, then that will give us erroneous results and erroneous predictions, which can mess up our guidelines, which can mess up our decision making, because simulation is often used in decision making in economics, in healthcare, in environmental systems, in biology, in medicine. For example, one of the spectacular use of simulation right now is not, I mean, definitely in environmental systems we are doing, obviously, but one that really blows my mind is the shift from in vivo experimentation in medicine to in silico experimentation. So we are able to simulate the processes within the human body or within the body of an animal. So you can understand it's not the body of the animal that we are experimenting on anymore. It is possible to do this on a simulation, a simulated reality of an animal's body or a human's body. So moving from in vivo to in silico is also possible because of advances in simulation. And it is not possible to go through all those advances, which takes years of rigorous training to understand in a course like this one. But what I'm definitely going to do is introduce you to different approaches. So let's get started. Now, before we move on to different kinds of simulation, let's very quickly list down the advantages of using simulation versus actually doing the experiment in real life. For example, in environment, why not do experiments on a real lake or on a real ASP-based wastewater treatment system? Why do it in simulation? First, it's going to be cost effective. Now, I'm using the word cost effective here, but please understand, it is possible to make very complicated simulation softwares or packages, which can be very expensive, even depending on how intense or how detailed and sophisticated the simulation package is. It is quite possible that the simulation is actually quite expensive. So here, mostly usual simulation softwares and packages are more cost effective than real life experiments. That's not always true. Second is that we can avoid risks and damages. For example, when we are giving training to our pilots, some part of the training goes into flying simulated airplanes, simulated helicopters. So they're in virtual reality and they're trying. And the mistakes they make there help them learn and avoid real life mistakes, which can be extremely risky and dangerous. So use of simulation can actually help us avoid risks and dangers, even in environmental studies and environmental systems. The third very important advantage of using simulation instead of doing the experiments in reality is flexibility. We can try out different scenarios. We can try out different scenarios in shorter duration for less cost and experiment to see what are the possible results of different interventions and different human activities in different environmental systems. The next advantage that simulation gives us versus actually experimenting in reality is ability to compress or expand time. So I would state it as that ability to study transient behavior. Now, there are techniques, simulation techniques, that allow us to expand or compress time, but there are also some simulation techniques that don't permit that. So, all of these advantages that I'm listing are in general associated with experimenting with simulations versus reality. But again, different approaches have their own pros and cons. Remember that. So, this includes expansion and contraction of time. Now, expansion and contraction of time are very relevant for continuous models. So, this is a model where time is moving linearly in one particular direction, and because of the movement of time, the system is undergoing a change. And these kind of models typically use ordinary differential equations, which are then integrated or analyzed or simulated using different mathematical techniques, and then we get a better understanding of the transient behavior. Almost the entire environmental modeling and simulation course focused on transient behavior of environmental systems, which is when, because of the passage of time, the behavior or the state of the system is changing. Now, what simulation allows us to do is to either expand the time or contract the time. Some environmental processes take over very long duration of time, like many decades, many centuries. Some, however, are really fast, like certain chemical reactions or certain biological activities such as growth of toxic algae. Our simulations allow us to play around with the speed with which time is changing, can really hasten getting the results, getting the predictions. Okay, the next advantage of simulation is that it really makes visualization very easy. Now, data visualization is a different thing. In simulation, when we visualize, we can see how our system is changing over time, and good quality visualization makes communication very easy. So remember, as environmental professionals, we need to communicate the results of our simulation, of our modeling with different agencies, our clients, and also people with vested interest and other parties. So communication is very important. Good quality visualization of your simulation can help with that. Okay, the other thing is all of these also lead to better decision making, comparing different decisions. So it helps us comparison. It also helps us observe diverse performance indicators. So let's just write indices. For example, in case of wastewater treatment, we have different indices or different parameters that we observe. We look at DO, we look at BOD, COD, we look at total nitrogen, different forms of nitrogen, phosphorus, and we want to look at all of them when we decide how effective our wastewater treatment process is. Simulation makes it easy for us to look at multiple parameters and also different performance indices for a system. And the other thing that simulation really helps us with is sensitivity analyses. As we are simulating a reality, we can change the values of different parameters that go into our model, and we can see how sensitive a model or a simulation is to a given variable, a given parameter. Now, these are all the pros. What are the cons? Well, the first con is that large scale processes or very complex processes, such as environmental processes, tend to be extremely complex. Even though simulation doesn't require typically the extent of simplification, which most models that we can solve and understand and grasp require, but there is some level of simplification that does happen when we are simulating. It is very important to remember or limit. So these are not necessarily cons, but these are limitations and constraints of simulated reality that we should remember. First is simulated reality is an imitation of reality. It is not the actual situation, actual state, actual environment. So there's even a slight error that is present in one part of our model, in one part of our simulation, that can give us erroneous results. We have to always be very cautious about it. This is where simulation validation comes into picture. It's very interesting for me that as I'm talking about cons, I'm remembering another pro that needs to be discussed in context of simulation. A model can be extremely complex, but very hard to understand, very hard to grasp. Only when we simulate the model, we can visualize the actual system, actual model, how it is working. So this is actually an advantage. Simulation can help us make sense of very complicated models. However, it is also not a perfect imitation of the reality. It's only an imitation. Okay. Next limitation or constraint or cons of using simulation is that they require high performance computational ability. Typically, not all of them, they're simplified simulations too. But if you're looking at complex systems, we require supercomputers, we require high performance computation ability. The other thing is that our simulations also need pseudo data or some kind of data to run the simulation. So the parameters that go into the model, we need to have estimates of them. We talked about this in previous lectures when I shared with you that when doing sensitivity analyses, we know that we don't have the exact value of the parameters, and that's why we do sensitivity analyses. With simulation, the same limitation holds true. We don't always know the exact value of parameters. We don't exactly have the data to feed through the simulation. So there is some error into the input that we give into the simulation, which is also another reason why we need to be very cautious regarding the first constraint, which is the simulation is not the reality itself, it's an approximation. There are inbuilt errors in every simulation, which doesn't make it not useful necessarily. What it requires is us to be cautious and informed. The other thing is that if the objectives, because I'm a researcher, I will say research questions or aim of your simulation is not clearly defined, it's not very useful. It's not really a con, it's not a limitation, but it is very important information for a person interested in simulation to have. Now let's look at different kinds of simulation strategies, techniques that we have with us. We can divide the simulation models that we have into multiple groups depending on their different features. One of the important features that we can use to split simulation models into two groups is whether they are static simulation models or dynamic simulation models. So let's look at this. So static models are solved once for a given time t. For example, if you remember in school, we learnt about how to calculate the velocity, the distance, the height of body in projectile motion. So let's say a body was put forth in projectile motion. We know at time t equal to 0, we know what the velocity was and the angle. So we basically know the velocity. And we want to figure out at time t equal to t1 exactly what its location is, this body's location, its velocity, and height from a particular surface, not necessarily the ground level, but height from a particular surface. So we can calculate, we can simulate this reality for a given time t1. This is an example of a static model. It is solved for one given time t, it's solved only once, and most of the systems, most of the simulations that are spreadsheet based, these are easy because we are just calculating, we are putting in the value for one given time. So most of the simulation models that are spreadsheet based are static models. Also, most of the Monte Carlo based models are also static models. Now, dynamic models are very interesting on the other hand. What they do is they add a time dimension. We can actually see how the system evolves over time. Now, since most environmental systems and also systems in economics, they change with time, time is very important. We assume that time is moving linearly in one direction. For economics, for environment, we typically use dynamic models, not always, but typically. The second way in which we can categorize the models is by calling them continuous versus discrete simulation models. So, continuous versus discrete simulation models. Now, continuous models, time is moving continuously. So, clearly they are time dependent. Time is moving linearly. They typically require some level of abstraction, decomposition, and aggregation. These are very interesting because, again, like dynamic models, they are time dependent. Time is moving in one direction linearly, time moves continuously. Now obviously, even though time moves continuously, we can, when we are actually running the simulation program, our continuous time can be discrete with very small time intervals. So we are calculating the model, the dynamic model, for very small increases in time, and here I have written delta t. So very small amount of time in discrete time intervals, time is increasing, but it overall gives the appearance of continuous model. Discrete simulation models are different. Discrete models are relevant when it's not time that causes the change in the system, but it is the event that causes the change in system. This is very important to understand. For example, let's say an event happens. Some pollutants are released into a lake, and now we are having fish kills, we are having eutrophication and frothing in the lake. We are modeling the change in DO. The DO is changing over time. So the model that we'll have will be a continuous time dependent model. It is the passage of time that is changing the DO because of biological activities, because of putrefaction and other things. However, in event dependent systems which use discrete models, it is the event that drives changes. For example, let's say we are looking at a traffic model, and the event here could be passing of the car under a bridge. So it's not time that is important, but every time a car passes under the bridge or passes through an intersection, the model moves forward, the system changes. So that is an event based model. The third way in which we can split our models into two distinct groups are stochastic versus deterministic. Now, stochastic models will have a probability based element to it. Now, this probability is not same as getting some data from a system that is normally distributed. That's not what we are looking at. Basically, stochastic models, their output for any given situation at any given time or any event is probability based. There are multiple possibilities, and each possibility has a probability attached to it. So there is no definite answer for any given situation at any given time for any event. Since the solution itself is probability based and there are multiple solutions possible, stochastic models tend not to be applicable when we need a more definite answer, which is where deterministic models come in. Now, deterministic models, what they give us is for a given time or a given event, they give us very specific answers. So there's only one definite solution. Now, while it may appear that deterministic solutions or deterministic models are more useful because they give us definite solutions, we know exactly what is predicted and we can take actions thereof, there are situations where a deterministic model will be expensive, unnecessarily complicated, or require resources that are not really needed, and that is when stochastic models are very important. For example, prediction of flood. While we want to have as good an estimate of when to predict flood, let's say in next 3 days, in next 5 days, if I'm trying to study, so that is where the deterministic model might help. If I want to look at, okay, what are the chance, or should we expect a flood today or tomorrow? That information we need it from a deterministic model. However, if I'm trying to study what are the damages that a flood which may occur this year or next year, let's say a 100-year flood, what damages it may incur in this particular region, then I do not need to know the exact time of the flood. I don't need to know the exact timing of the flood, the exact behavior of the flood water, but a stochastic approach which would be simpler, more cost effective, would be good enough for me to understand what kind of damages and what kind of interventions are required when the flood does happen. So this is where stochastic models are very, very useful. The other thing to understand about stochastic versus deterministic models is that in deterministic model, no matter how many times I run the model, I always arrive at that one definite solution. But because stochastic models are probability based, there's a possibility that every time I run the system, there is a slight difference in the output or even a significant, substantial difference in the output. So, stochastic models are typically run multiple times, and then looking at, okay, I ran it 1000 times, how many times did the output A happen, how many times did the output B happen, how many times C happened. That helps us get the probability of different possible outcomes. All of them are possible, but it requires multiple runs to arrive at the probability. Now, another feature with deterministic model is that we only can use deterministic model where we have all the information about the system. So it requires complete information or near complete. So we should know all the parameters, we should know the exact location at a given time. So the initial conditions should be extremely clear. Stochastic models will work even when we do not know everything about the system. There's a very famous example in physics where people were trying to understand how the atom's movement, Brownian motion, changes with temperature. And doing it via deterministic model was extremely complicated because there are so many atoms in a given space, in air, in atmosphere, and how they interact with each other, what the different forces are of attraction and repulsion and the collisions that they go through. So deterministic modeling was nearly impossible. However, the stochastic approach became very simple, and that's where the Boltzmann came in with his Boltzmann formula. So, deterministic model require complete information, stochastic don't. And as I said, the Boltzmann equation is an example of how stochastic approach helps us understand the behavior of the entire system without giving specific answers for each given entity in the system. If you look at our graphical approach, even though it is not stochastic approach, it's not probability based, it gives us an understanding of the qualitative behavior of the system, not quantitative. So it's not exactly the deterministic model either. All right, students, this is all for today. In the next lecture, we will look at different simulation approaches. Thank you.